Well, hello, good morning, or good afternoon. Might be Monday, might be Tuesday, happy whichever. All right, so by now you have received an email from the school explaining our new schedule. So let me just go over a few highlights with you in case you haven't looked at it or realized where we're going to go with it. They've essentially instructed the teachers to give 4 days of instruction, Monday through Thursday, in about 30 minutes a day. But then they've also said that you're working with certain class periods on Monday and certain class periods on Tuesday. So that could be interpreted as an hour lesson on Monday for some classes, an hour lesson for the other classes on Tuesday. It's confusing. So really what we're going to do is make it the equivalent of an hour every 2 days. So whether that means we give you an hour on Monday and then you distribute over Monday and Tuesday, or break it into two parts Monday and Tuesday, that may vary. So what I'm going to shoot for here is I'm going to shoot for about a half an hour on this file, and then we'll do another file for another half hour. That'll be your Monday and Tuesday. There is a half hour every day where the teachers are available online, FaceTime, or obviously Meetup or Google Meetup, where every class gets 1 day, half an hour on one of the days of the week. You know what? If I'm online, go ahead and check in, even if it's not your day. I don't care. I'd love to see you. That's fine. Then there's another couple of hours a day where the teachers are, quote unquote, available for the students, meaning we're checking our email, replying to emails, things like that. That's separate from the Google Meetup time. So look at the schedule. It's broken out a little strange, but essentially, I'm available when you guys need me. Mr. Zarzak's available when you need him. Email us, show up at that FaceTime or the Meetup time to chat and talk and ask questions and see everybody else and say hi. It's not required for you, but highly recommended you pop on in and at least say hi. I'd like to see you guys. So that's kind of the schedule. So this file here is for Monday itself. We'll have another one for tomorrow, for Tuesday. So this should be about a half hour or so. So a little lecture and then a couple of practice problems. The practice problems will be on Socrative, so that should be up and running by the time you see this. And it has enough questions to cover Monday and Tuesday. So it's one big Socrative for those 2 days. At least that's our plan currently. This is Friday. Plans, of course, could change. All right. So that's the route we're going to go. And we're going to jump on in with, of course, your target tallies.
I'm in my classroom doing target tallies with my teacher. I'll be super smart by the next test.
Yeah.
I'll be smarter by the next test. By the next test, switch up to my homework. Finishing my chapter outline. Remember target tallies, I'ma do fine.
Yeah.
I know I'ma do fine. I'ma do fine.
Okay, so part of this is a little bit of review from that VIR lab that you did. So you made a graph, or a couple of graphs. You had a voltage versus current. Remember, the variable for voltage is V. The unit is volts, which is also V. Then you've got current. The variable in equations for current is I, but the unit is amps, which is a capital A. So volts is the only thing we deal with that has the same letter for unit and variable. Remember, everything else has different letters. Don't put A for a variable. A is not a variable. I is a variable. Okay, so you got your graph. And you plotted your data points, and you did a best fit line. Now, for the resistor, hopefully your line got somewhat near the origin. You didn't have to. Remember, you never force things through the origin. And you had the slope of that voltage over the current. When you took that slope, hopefully you found that slope was awfully darn close to the resistance that was on that resistor in the lab. So if you had a slope of 250 or a slope of 500, hopefully that resistor was about 250 ohms or 500 ohms. So that means we can rearrange that equation, solve for V, gets rid of any denominators and fractions, and you get V equals IR, which is what we're going to call Ohm's law. Hey, V equals IR. The lab name was VIR. What a coincidence! So Ohm's law basically says that if you have put a voltage through a resistor with a resistance of R, you'll get a current I. All right, that's it. That's the deal. Any object that gives you a nice straight line graph, we consider that object to be ohmic. So when you graphed your resistor, hopefully you got a straight line, because resistors are designed to do one thing and one thing only. keep a nice constant resistance as you pump more and more voltage through it. You get a linear relationship between the voltage and current. Now, obviously, at some point, you're going to put too much voltage through it, you're going to fry the thing, it's going to get destroyed, and all the rules will change. But the equipment we're using doesn't do that. It doesn't go high enough. So resistors are ohmic, meaning they get a nice straight line when you graph out voltage versus current. The light bulb, on the other hand, you should have noticed the data was not linear. In fact, it should be something of a curve, and you get an increasing slope as that goes along. So a light bulb is not ohmic. Now, that doesn't mean you can't use Ohm's law for it, V equals IR. At any particular voltage, you'll get a certain amount of resistance and you'll get a certain amount of current. It's just as time goes on and you crank that power higher and higher and higher, you're going to get a different relationship between them. The resistance is not constant. But for that instant in time, that particular moment, you get, hey, there is a relationship. It's just not a constant relationship as you change it. And that's because as a light bulb gets more voltage through it, more current through it, it gets hotter and hotter and hotter. And as it gets hotter and hotter and hotter, the resistance changes. Pause, think for a moment. Previous discussion, we talked about resistance of an object based on its size and shape, certain cross-sectional area, certain length, certain material. If this doesn't look familiar, pause this video, go back, look at your notes, look at the last video. It talks about a relationship or the resistance of an object based on its size, shape, and material. There was also a temperature formula. I mentioned certain materials, as they heat up or cool down, resistance changes. That's exactly what you're seeing here with the light bulb. As that light bulb gets hotter and hotter and hotter, that resistance changes, and that's that equation that I shared with you for temperature adjustment. Light bulbs are actually designed to do one thing really, really well. They get hot. And the light is a side effect. 95% of the energy goes into generating heat, about 5% goes into light. So they get hot. Temperature changes, the resistance changes. Okay, so light bulb, not ohmic. All right. So voltage measured in volts. Variable is V, the unit is V. It's the only time they're the same. Current variable is I. It's measured in amps. The unit is A for amps. Resistance, the variable is R. So on the left-hand side, you got your voltage equals current times resistance. It's V equals IR. But the units for resistance are ohms. That omega symbol right there is the symbol we used for the unit, omega for ohms. You don't have to write out the word ohms, OHMS. Just do that symbol right there, and that is really all you need. If you want to write out the word ohms, you can, but most of the time we're looking for this symbol. So it's going to be a long, it's not going to be a long week. A nice relaxing week. So let's relax. Let's meditate. Om. Nope, you're not saying it. You got to say it. Om. Nope, almost everyone said it. Not quite everybody. Try it again. Om. Oh, everyone but Bill said it. Come on, Bill, you too. Om. Okay, close enough. All right. By the way, if that's an ohm, what's this? It's a mobile ohm. Hey, if that's a mobile ohm, what's this? It's a mobile ohm pulling a Volkswagen. Hey, then what's this? It's a mobile ohm pulling a Volkswagen with a current plate. Yeah, we spent a long time putting it. You know what? That mobile ohm joke, I actually first heard that joke back in high school when I was a senior. And it was one of those groaner jokes like, oh, wow, that is really bad. And I carried that joke in the back of my head for 30 years. Never had any use for it. Couldn't share it with anybody. Would not make any sense to anyone. And then I became a physics teacher. I dusted off and said, I can use this 30-year-old joke. I was very pleased with myself. All right, moving on. Okay. So now you know what happens if you've got a single resistor and a single power supply. You get a voltage from the power supply, the resistor gives you a resistance, and you get a certain amount of current. V equals IR. All good for one resistor. But what if you have multiple resistors? So here we've got a battery, and we have three resistors in a row. We're going to call that in series. We'll talk more about that later, but they're in a row, they're in series. So, okay, great. What's going to happen? Well, the battery is going to try and push current through the system, and the resistors are going to resist that current going through the system, because that's what resistors do. So we want to figure out how much current we're going to get. To know that, we need to know how much resistance we have. So think about what's going to happen here. The battery is giving you a voltage, it's giving you a potential difference, and you're going to have a potential difference drop across one resistor, some across the second resistor, some across the third resistor. So each of these resistors will take a little bit of voltage potential away from the circuit. Think of it this way. That battery lifts it up. In this case, let's say it's a 12-volt battery. That battery lifts us up and gives us a 12-volt potential difference from the negative end of the battery to the positive end of the battery. And then we get a voltage drop across the first resistor, voltage drop across the second resistor, and then a third voltage drop across the third resistor. And now we're back where we started. And now the battery lifts us back up again. You can almost picture it like a fountain, like a water decoration, a fountain decoration in the backyard, where you've got a pump that pumps up the water to a certain height. And then you've got 3 waterfalls, and each one lowers that potential of the water. Now in this case, each of these is showing a 4-volt drop. You go from 12 down to 8, 8 down to 4, 4 down to 0. It's the same drop for each resistor. What do you think has to happen in order for it to be identical drops for each resistor? Now, I'd ask the class here, think about it for a second. If you guessed that the resistors have to be identical, you'd be correct. If the resistors are identical, you get an identical drop across each resistor. And it doesn't matter what the resistors are. They could be 1 ohm, 10 ohm, 1,000 ohm, 1,000,000 ohm. As long as each resistor is the same, then they're going to have the exact same voltage drop across them. So those voltage drops will add up to 12, and the battery gave us 12 to start with. The total increase you get from the battery has to equal the total drops you get from those 3 resistors. In AP, we learn about something called Kirchhoff's law, which basically says the sum of the voltages around a loop has to equal 0. Okay, well, you get a plus 12, minus 4, minus 4, minus 4 equals 0. So we can think about it that way as well. Now notice we're measuring the voltage difference across the resistor, because you're checking the voltage on one side, check the voltage on the other side. The voltage difference is 4 volts. We don't actually care if one of them's 12 and one's 8, and then here it's 4, and then here it's 0. No, we don't care about that, because odds are they're actually not those numbers. All we care about is the difference on one side versus the other side. Now, what if the resistors aren't the same? Okay, so now here we've got 3 resistors, a 4 ohm, an 8 ohm, and a 12 ohm resistor. They're lined up one after the other, and you got that 12-volt battery there. And we want to know what is the total resistance of the circuit. Now, at this point, Socrative should be up and running. I think there's 5 questions you're about to answer today with this particular lecture file. So go ahead and pause this, go to Socrative, log in, and enter your answer there. Okay, now you can just easily jump ahead, see the answers, and plug them into Socrative. Remember, you're not being graded on Socrative. The whole point of this is to see if you can do it. So do test yourself, give it your shot, and then see if you got it right or not, okay? So, of course, the answer is 24 ohms. Because the resistors are added up. When they're one after the other, remember that the calculation for how to get resistance in the first place for an object, the longer the object is, the bigger the resistance of the object. Well, picture these resistors just being end to end to end to end to end, which means when they're end to end to end, you just end up with a longer resistor. A longer resistor is a bigger resistor. So the longer it is, the more resistance. So because they're end to end, we just add them up. So 24 ohms. All right, so now we know that that voltage out of that battery is 12 volts, and that total resistance that it has to push current through is 24 ohms. So if your total voltage is 12 volts, and your total resistance is 24 ohms, using your new equation, Ohm's law, what is the total current going through the circuit? Pause the video, give it a shot, enter it in Socrative, go. Okay, so if you do your voltage is 12 volts, your resistance is 24 ohms. You get your 12 volts divided by 24 ohms, you get half an amp. What that means is you have half an amp of current going through this circuit. As a comparison, a 60-watt light bulb in your house would have about half an amp going through it. 120 watt light bulb, which you probably don't have a lot of. Those are really bright, maybe a 100 watt light bulb. A 100 watt light bulb is almost 1 amp. So a 60 watt light bulb is really close to half an amp. So that's an idea of how much current you have. If you had half an amp going through your body, it would kill you dead. That is way too much current for the human heart to handle. Fortunately, we try and avoid that. And we can't do it in this lab. Because just because this circuit has half an amp, it doesn't mean it would go through you. If you were in that circuit, your resistance is way bigger than 24 ohms. So picture thousands of ohms of resistance, much, much less current. So this 12 volts is not going to hurt you. All right. So here we've got our current going through our circuit. Now think about that current. Current is the flow of electricity. It leaves the battery, half an amp. Goes along through the wire, half an amp. Goes into that first resistor, half an amp. Comes out of the first resistor, still half an amp. Picture water going through a hose. That water's got to go through the whole hose. So this current's going through the whole circuit, same idea. So half an amp through the 12 ohm, half an amp through the 4 ohm, half an amp through the 8 ohm. And then back in the battery again. So to be more specific, this was the total voltage, total resistance, total current. So I highly recommend you put little subscripts. So there's your V of t, I of t, R of t. And the reason for that is we're going to be looking at individual pieces of a circuit, maybe resistor 1, resistor 2, resistor 3. So they would have V1, V2, V3, R1, R2, R3, etc. So this is very specifically total battery, total current, total resistance. Thus those little subscripts. Alrighty then. So now we know the total current going through each resistor. So, since it's the same current going through each resistor, each individual resistor gets its own Ohm's law formula. So you've got the voltage across the 12 ohm resistor, the current through the 12 ohm resistor, the resistance of the 12 ohm resistor. Same for the 8, same for the 4. So your next talkative question: if the current going through that 8 ohm resistor is half an amp, and the resistance of the resistor is 8 ohms, what is the voltage drop across that 8 ohm resistor? Again, we use Ohm's law. By the way, Ohm's law, we're going to use that every other calculation. We might calculate something with Ohm's law, and then power, then Ohm's law again, and then something with series, then Ohm's law again, and something with parallel, and Ohm's law again, and then something about a light bulb, then Ohm's law again. Ohm's law is the most common formula. Use it about half the time because we keep going back to it. All right, so go ahead and do that calculation. Put it in socrative. Pause the video here. So this time, when you use Ohm's law, you do V equals IR, but we're not going to do VT, IT, RT. We're not doing total voltage, total current, total resistance. We're doing that 8 ohm resistor. That 8 ohm resistor has half an amp going through it. And if you do V equals IR, and you've got your half an amp times your 8 ohms, you get a voltage of 4 volts. Okay, and that's just using Ohm's law for a single resistor. So we can use Ohm's law for the total circuit. We can use it for a single piece of the circuit. It still works. So Ohm's law is a very, very useful tool. You'll be using that a lot. All right, so let's give this next one a try. Using what you've learned, what is the voltage drop across the 4 ohm resistor? Remember, it's that same current everywhere in the circuit. So pause the video, give that a shot. And then finally, your voltage drop across the 12 ohm resistor. Pause the video, plug that in. All right, so you would have had 4 volts for the 8 ohm resistor, 2 volts for the 4 ohm resistor, and 6 volts for the 12 ohm resistor. Add those up. You get 4 plus 2 plus 6 is 12 volts, which is exactly what the battery is. So those are voltage drops across those resistors, decreases in electric potential, whereas the battery gave us a voltage increase. And remember what I said about Kirchhoff's law earlier, sum of the voltages is 0. So you get the plus 12 from the battery, and then the minus 12 total from those 3 resistors. That's the idea. Okay? So this is the resistors in series. Here's your series circuit rules. The total voltage equals sum of all voltages. So your total voltage of the battery equals the 3 voltage drops in those resistors. Obviously, if there was only 1 resistor, you'd have 1 voltage drop. It would be the total value you had for the battery. If there were only 2 resistors, those 2 voltage drops would add up to your battery. Total current, same current throughout in a series circuit. So no matter where we measure that current, we're going to get the same value. Remember how we use the ammeter? You break the circuit, insert the ammeter. So if we put the ammeter just to the left of the resistor, just to the right of a resistor, to the left or right of the battery, between any pair of resistors, you're going to get that same current. Total resistance, sum of all resistors. So we add up those three resistors, and that gives you the total resistance for that series circuit. There's rules for series.